You ever wonder how a self-driving car just knows how to stay in its lane? Or how a simple thermostat keeps your room at exactly the right temperature? Well, it all starts with a special kind of language. It's about turning the real physical world into math so we can predict and, yeah, even control what happens next.
So how on earth is that possible, right? How can we take a really complex, kind of messy system, like, say, the suspension on your car, and boil its very essence down into an equation, and then use that simple equation to predict exactly how it's going to behave out on the road?
To get to the bottom of that, here's our game plan. We're going to start with the real basics, static versus dynamic systems. Then we'll look at how you model them, see how those models are all connected, and finally wrap up with why any of this really matters in the first place.
Okay, let's dive right in. The very first thing we have to do is make a really important distinction. Whenever we look at a system, we've got to ask one simple question. Is it just sitting still, or is it actually in motion? So on one side, you've got your static systems. The best way to think about these? It's like a photograph, a single, frozen moment in time where everything's perfectly balanced. And since nothing is actually moving or changing, we can use good old algebra to describe it. But then you've got dynamic systems. And these are all about change. They're like a movie, not a photo. To capture things that are constantly in motion, changing their speed or position, we need a more powerful tool, and that's calculus.
So let's talk about that static snapshot. How do we actually capture that single moment and lock it down with math? Let's break it down.
The process is actually pretty straightforward. It's really just a logical three-step journey that takes us from looking at a physical system to getting a super precise mathematical answer. All right, step one, we have to define the system with its core equation. The best way to think of this is like a recipe. U is your input, that's what you're putting into the system. X is your output, what you get out of it. And all those other letters, the A, B, and C, those are the system's parameters. They describe the system itself. Things like how stiff a spring is or the resistance in an electrical circuit.
Now, once we have that relationship laid out, we can do a little algebraic shuffle and get to the solution. And this new equation is incredibly powerful because what it's saying is, hey, just tell me your inputs, your U, and I will tell you exactly what your outputs, your X, are going to be.
Okay, so how do you actually calculate the answer? Well, there are basically two main paths you can take. First, you have what are called direct methods. Think of this like having the perfect key to a lock. You use techniques like matrix inversion, put the key in, turn it once, and boom, you've got the exact answer. One clean shot. Then there are the iterative methods. These are more like picking the lock. You start with a pretty good guess, then you just keep refining it, tweaking it, getting a little closer and a little closer with every single attempt until you're right on the money.
But here's the thing. Most of the really interesting systems in the world, everything from a rocket ship to the stock market, they're dynamic. They are always changing. And for that, we're going to need a much more sophisticated set of tools. And it turns out there isn't just one right way to describe a system that's in motion. Instead, engineers use this trio of models, three totally different mathematical languages that all tell the exact same story, just from a different perspective.
First up, we have the differential equation. This is the most fundamental, nitty-gritty view. It's like the system's autobiography, written in the language of calculus. It describes every single internal change, every interaction, at every single moment. It's the complete, unabridged story.
Now, the second language is the transfer function. So if the differential equation is the whole novel, the transfer function is like the brilliant one-sentence summary on the back cover. It completely ignores all the internal details and just focuses on one thing, the direct relationship between what you put in and what you get out. It is incredibly efficient for a high-level view.
And our third language is the state-space model. This is like having a perfectly organized spreadsheet for the entire system. It tracks the absolute minimum number of key internal variables. We call that the state, that you need to know to predict the system's future completely. It's really the perfect blend of internal detail and organized structure.
But here's where it gets really cool. This is the most powerful part. These three languages, they aren't isolated. You can translate between them fluently. An engineer can just move between them seamlessly.
And this right here is where the true genius of system modeling lies. An engineer can start with whichever model is easiest to build and then just convert it into the model that's best suited for solving their specific problem. It's incredibly flexible.
So let's see how this actually works. For example, by using this really clever mathematical tool called the Laplace transform, we can basically translate the complex calculus of the differential equation into simple algebra. This lets us create that much cleaner transfer function. We're essentially trading all that internal detail for high-level clarity.
And you can go the other way too. We can take that compact transfer function and we can sort of unpack it. This lets us build that highly structured state space model by calculating the exact matrices, the A, B, C, and D, that define how the whole system works on the inside.
Okay, so we've got 3 different models, and we know we can convert between them. But why go to all this trouble? Why not just pick one and stick with it?
Well, the answer is that each model is a specialized tool for a very specific job. Let's say you need to build a hyper-realistic flight simulator that has to account for every single physical force. The detailed differential equation is going to be your best bet. But what if you just need a quick high-level check to see if your new airplane design is stable? Is it going to fly straight or spiral out of control? The transfer function gives you a super fast answer. And for designing the incredibly complex flight controls of a modern jet with dozens of inputs and outputs, well, the highly organized state space model is the absolute industry standard.
So ultimately, being fluent in all 3 of these languages is what allows engineers to be such versatile problem solvers. It lets them analyze, simulate, and design with incredible precision, building the robust, predictable systems that our whole modern world relies on.
And that kind of leaves us with one last big thought. These models give us this incredible power to predict how things will behave. But as our models get better and better, we really have to ask ourselves, where is the line between prediction and absolute control? Definitely something to think about.